All right, folks, to recap what we've been doing last week, the data link layer, I'm just going to step back and go through that little data link in action, if you will. And remember, I walked through this little PowerPoint with you guys explaining, all right, we have the logical link control and we have the media access control. The media that's connecting us in this classroom is the air, correct? And instead of using sound to distribute the data, I used light waves. So I had a slide that was going to be black or a slide that's going to be white. You guys had 5 seconds to write down this code. So it looked something like this. And then it would just page through. Don't worry, we're not going to waste our time going through this again. You guys have it written down. It was a very long, tedious process. What could I have done to improve the actual performance of this transmission? Yeah, so instead of setting it for 5 seconds, I could have made it a second. But what's going to dictate that? Yeah, basically you guys could have went up there, looked at it, then came back on your notepad. What else could I have done? And it's not a new concept, but we're going to revisit this. See, lately in computing, everything's been like serial, and a lot of people think serial connections are the fastest. Well, that's not necessarily true. The reason why our hard drives have moved to serial connections is because of interference at higher rates. So we burst the bits in line with each other, one after another, at extremely fast rates. But back in the day, we had parallel connections. And we would send many bits at one time. But the problem with doing this is you'd have interference. So you couldn't send it too fast. Because the faster you send something, the more voltage it would take, the more prone it would be to interference. Could I have split my slides into 4s? And then do like white, white, black, white, or whatever the zeros were. And so when I flashed it with you, you would write 4 at a time. And that would be considered parallel processing, if you will. So there's all these different techniques out there to go with it. In the process of this occurring, were you guys allowed to flash me? Were you allowed to take your flashlight and then give me some kind of signal? No, I put that in quotation, so let's put it in perspective here. You know, here I am, the PowerPoint's flashing you with black or white slides. Could you do that too? Could you turn your monitor around and flash me with black and white slides? What's this? When it's your turn? Yeah, it all depends on the rules that we establish. Now, if I'm flashing you and you guys can't flash me at the same time, this would be considered half duplex. We clear about that? One direction at the same time. So I'm sending, you're receiving, and then I wait, you send, and I receive. It is quite possible because I don't really need to care what I'm sending out there because I know what's going on. My eyes are towards you. I'm not paying attention to that. So you guys could have flashed me. The problem is I am one and you are many, right? So who could have flashed me would have been the issue, correct? And we call this contention. That you guys are competing to use the same medium. Now in point-to-point networks, we don't worry about that. Because I know that there's only one other node that's going to be accessing this medium. The other node at the other end. We good about that? So today I'm just going to go back to go over what we've done. And you guys, if you didn't bring out your workbook, just go ahead and write this. But don't write it vertically like I wrote this. Just write it in a string. And write them all out because we are going to dissect them. And if you need to go back to another line, give yourself some space between those 2 lines. And the reason why I'm having you guys write this out is I want you to see the structure that a data link protocol establishes to transmit a frame. Now remember, a frame is what we encapsulate a packet into, correct? Yep. Packets come from layer 3. And why do we concern ourselves with frames? What is the purpose of a frame? Exactly right. And I couldn't have said it any better myself. Frames are specially tailored to handle the given medium used to interconnect devices together locally. So what types of mediums can we use? Well, in this example, we used the air. What signal did I use to carry the message in this previous example? Light waves, right? Could I have done something slightly different instead of using black and white? See, in the world of computing today, we're just dealing with binary, two distinct values. It's either going to be black or it's going to be white. There are 16.8 million colors that you and I can detect. More exist, but we can't see them. Could I have color coded this? Absolutely. Would have saved me any transmission time, because I would still be stuck with one color per slide. Would have caused you guys some extra thought process? Okay, no, wait. He said black was white. Or sorry, no, black wasn't white. Black was 0, white was 1, and pink is 2. And the more elaborate I make my encoding mechanism, what does that mean about processing attention? The more time it's going to take. So we like this discrete nature. It's very simple. The other thing that we like about it is that, hey, we can go really far distances without wondering, is that a blue or a purple? Correct? It's black or it's white. More importantly, you either feel voltage or you don't. Correct? So as you guys are writing this all out, I want you to understand that this mechanism that I use to deliver this frame to you is what I made up. I try to follow certain rules. That is, there's going to be a beginning of the frame, which we call the start of the frame, right? SOF. And Ethernet, we call this the preamble. The other thing that's going to be in there is going to be addressing mechanisms. Types. The type field's very specialized. It's going to let me know what network layer protocol was this frame destined to go to. Interesting. The data link layer handles two parts. Logical link control, as well as media access control. The logical side is where we bridge all the software to the hardware. The MAC side, the media access control, is basically representing the addressing and placing the frame on the media. I know we passed that down to the physical layer. That's why a lot of people like the TCP/IP model, because remember, the lower layer was the network access layer, and that consists of the data link and the physical layer from the OSI model. So it was really simple. It was just done right there. So I say this because the data link logical control allows us to handle more than one network layer protocol on the same network. That is to say, this computer up here could have IPv4 installed on it, and this computer right next to it could have IPv6 installed on it. And it's not going to cause any problems with my network. This is why I'm telling you guys, and I believe I told you maybe 2 weeks ago, that Comcast and Time Warner are experimenting with letting out IPv6 out there on the network. Should they worry about it? No, the data link layer says, no big deal. If you receive a frame that was destined to be passed up to an IPv6 layer protocol, and you don't have that installed on there, that data link layer will detect that and discard the frame. Why must it discard the frame if IPv6 wasn't installed on your computer? Well, when we get to the layer 3, what are we trying to determine? Does my logical IP address match the destination IP address of this packet? If it doesn't, what are you supposed to do, quote unquote, with the packet? Drop it. But if you don't understand how to interpret where or what these bits represent, i.e. you don't have that protocol installed on your computer, what's the point of trying to read it? So it's discarded. Very nice feature. So we're going to dissect this. Does everybody have this written down now? Okay, good. So here's a general model that I was trying to follow. This is a classic Ethernet frame. You can see that I have the preamble, which we would call the start of the frame. I'm trying to keep it generic. These are examples that are implemented in everyday's network. But we're just saying start of the frame, no problem. Destination and source, those are the physical addresses, right? Now in Ethernet, we commonly call them MAC addresses. Generically, you'll find out why we stick to that, because down here we just call it an address. Type is going to determine that upper layer protocol, IPv4. By the way, just for your notes, when you're using Packet Tracer, and you're walking down through the PDU details, remember that little thing that we did way back in the day? You clicked on an envelope, window popped up, and you can click on the details. In type, if we are using IPv4, it'll show up in a hexadecimal format as being 0x0800. Okay? Now, I took time out of the class to explain that to you because that might be testable. So, in there, we would actually represent that as binary. 2 bytes, which would be 16 bits, correct? What do you think the data is going to consist of? There is a cap and there is a minimum. I'll explain that in Chapter 9. But what do you think the data contains at this moment? And it will always contain this in a frame, whether it's an Ethernet frame or a PPP frame. What's that? It's going to contain headers, but more importantly, it's going to contain the previous layer's PDU. Correct? So this data is no different than saying it's the packet, because packets are what gets encapsulated into frames. Clear about that? And then inside the packet, there will be a data section. And what would be contained in a packet's data section or data field? A segment or a datagram, depending on what protocol you're using for layer 4. Does this make sense? And inside that segment, there will be a data section and will be contained in that data section. This is the only time that this section is actually appropriately named. Data. All right. And then the last one, the frame sequence. We call this the trailer. Ethernet frames use CRCs. All right. That's, if I can pronounce it, I always mess this thing up. It's like the metrics and matrix with me. Cyclic, hey, I did it. Cyclic redundancy check. Way to go. For all my students in the past, I learned. So it's always embarrassing because I'm always want to say something different. But CRC is basically some error checking algorithm that they look at the previous zeros and ones, they calculate it, they're going to get a number. They're going to match that CRC with what's stored in the trailer. Now you notice we're calling this the frame check sequence because every layer 2 protocol will have its own mechanism. Sum it all down to one simple word, it's just error detection. That's all. Why is it placed at the end and not the beginning of the frame? Why is it saying to it, hey, look, my error code should be this. Any bits that come after me, process that. The moment that the data is passed to the data link layer and the logical link control has established the framing mechanism that's going to be used, the media access control is going to start laying down bits to the physical layer. All right? These bits are going to travel. They're going to end up to another device. Whether that device is supposed to get the frame or not, it's going to end up there. All these devices that are getting these bits are going to buffer them up. How do they know where a frame begins and where a frame ends? If I just jumped right in the middle of that PowerPoint, those black and white screens, how do you know you received the whole entire frame and not parts of it? There's got to be some kind of beginning pattern, which we call the preamble. And in Ethernet, it was 1, 0, 1, 0, 1, 0, and that does that. Oh, let's see, 8 times 8 is what, folks? 64 times, except at the very end, it's going to be followed by a 1, then another 1. You can think of this as a beat, a drum. We're just tapping it. Boom, 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 boom. You guys should now fill in the blanks, right? You should have that pulse. We should be synchronizing. If I keep on doing that, eventually you guys are all going to catch on tune. But then at the end of it, instead of me going boom, waiting, and then doing another boom, I do boom, boom. Because you were expecting a pause, then a boom. But what I did was I went boom, boom, letting you know, let's begin. If you're checking that pattern and that doesn't happen, then it's safe to assume what? You got in the middle of the conversation. So you're going to keep on doing that, looking for those 64 zeros and ones that go boom, 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 and then boom, boom. I feel like some 8-bit video game. All right? But you guys getting the idea? Once you get that, things start buffering up. And now you're saying, and you're assuming, if you will, that everything from here on out is important stuff. But you're not sure if it transmitted properly. So you wait to the very end. If you have a preamble, what do you think you're going to at the end as well? Yeah, some kind of end of frame sequence. And maybe it'll be the opposite. Instead of starting off with a boom, there's a pause, then a boom. And it's going to be the same kind of bit patterns that I've had. The very first 4 bits, does it go 1, 0, 1, 0? Does your last 4 bits go the opposite way? 0, 1, 0, 1? So that's my way of letting you know that the frame began and the frame end. So here it is, to break it all out. The very first 4 bits are the start of the frame. The very last 4 bits are the end of the frame. These bits right here is going to be my error detection, my frame check sequence. Now, if you were to convert this number back into decimal, this is my CRC algorithm. If you convert that number back into decimal, you should get 21. Is that what you guys get? Nice little practice for you. What does that 21 represent? That to the left of this, all the way over, you're going to get 21 ones. Now, it's not the world's greatest checking algorithm, I will admit to that, but it's simple. It's enough for you guys to understand that you can start counting this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Oh, did I mess up? Was it 19 or 21? Remind me, folks. Was it 21? Did I just overskip something? See, I have 2 here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Oh, no. I think
you said it was 23, not counting the last.
23. That makes sense. Let's check this out. Let's convert this. That's 23. See? You guys shouldn't believe me. It's a Monday morning. I make mistakes. That's 23. And so if I do count up my ones, it's 23. It's not perfect. Why do I say it's not perfect? Well, if I didn't know how to count, for one thing. But secondly, what if I had a 1 here and a 0 there? Would I still have 23 ones? Absolutely. Was the 1 in the wrong place? Could that cause problems later on? Hey, places have values, right? 2 raised to the first is 1. 2 raised to 2 is 4, and so on and so forth. So 2 raised to 1 is 2. So when we look down through this and we're doing the error checking, it's not perfect, and it's not designed to fix anything. This isn't error correction. This is error detection. If I come up with 1 missing, what am I going to do with the frame? Discard it. All right, the next section, if this is the preamble, you'll notice I have all 1s. In Ethernet, this is the destination MAC address. What have we learned in Chapter 6 when the host portion contains all 1s? What type of address was this? Broadcast. I'm sending this to you guys, to everybody. So everybody would actually accept this frame. We good about that? Does that mean everybody is going to respond back to this? Can you answer that question given the information that you have right now? It all depends on what type of logical address is in the packet, correct? If the logical address was a broadcast address, would you guys then respond to it? If it wasn't, but rather a unicast address, would you guys respond? Would everybody respond to it? No. Only that person who has it. Notice the frame would pass it up to layer 3, correct? What would layer 3 do if it wasn't you who had that same IP address? Drop it. See the significance here? You guys are all seeing it come together. All right, so if this is the destination, what do you think these bits are going to be? By the way, in Ethernet, it's 48 bits. It's typically wrote out in hexadecimal, but I just figured make it small, short. What would this be if this is a destination MAC address? It's my address. All right. These 2 bits here, that becomes the type, letting me know what protocol is going to be used in the other layer. Then I have this 1 bit there. My QoS isn't as evolved. A 0 means off or low, and a 1 means high. Okay? 1 bit. Typically, other QoS protocols are going to be much, much larger, so you can say small, medium, large, if you will. More bits, more ways to encode. So then I have these 4 bits, and then I have these other 4 bits. If I just got done passing the QoS, where am I entering into now? I should be entering into the data, into the packet area. But I'm not going to explain that too much. I'm just going to skip back over the end. As you guys already saw, I have my trailer, I have my my end of frame sequence, and I also have my error detection. Are we clear about that? Because what I'd like to do is be able to wrap everything up from layer 7 down to layer 2. See, layer 1 just falls into place. All layer 1 will be is like somebody holding a flashlight and flickering zeros and ones. We good about that? So layer 1's very simple. The nice thing about layer 1, we get into chapter 8, is we're going to learn how to build cables. We're going to be making straight through cables and crossover cables. In fact, that's one of the most fun things you guys do in this course. Probably the only fun thing you do in this course, other than VLSMs. But in any case, you build cables, you connect these things together. You're actually getting into the physical interfaces. We're skipping over that. We're going to be coming back to that towards the end of the semester, only because I want to get you guys in the iOS and give you some more time learning the operating system for Cisco routers. Everybody's clear with this. I want to make sure I get these due dates so you guys have an understanding of what's going to be expected. All right, so let's see this in action. Just to explain it, up here in the area that we can't see, I'm going to have that frame for PPP. Now, PPP is short for point-to-point protocol. Okay? Where in this diagram am I going to use the point-to-point protocol? Am I going to use it in network A, B, or C? Network B, why is that? By the way, do I have to? See, some of you might see that this is a serial connector, and you might say, well, you have to. Why make it elaborate? I mean, my explanation was a marathon long when it could be real simple. What dictates all this extra overhead? Well, it depends on how you logically configure your nodes, how you arrange them together. Like if I were to use a hub here to connect all these devices together, what type of logical topology would that represent? If this had a hub here. Now you need to understand the concepts of logical because that allows us to see how the frames are being passed on. That's a hub. What does that indicate? That when I put a frame on this wire, on this medium, everybody gets it, correct? If everybody's going to get that frame, what type of media access control must I have to coordinate with? I'm sharing it, right? This is shared media. If I'm sharing it with it, then I have to be concerned with contention. If I'm concerned with contention, then what am I worried about? Collisions, right? What else should I be worried about if this is a shared medium? What else should I be worried about if this is a shared medium? Remember, exactly, but maybe in a lesser extent. I'm not too worried about security as much as I'm worried about identification, right? Because if I'm sending out this frame on this medium, and I wanted to send it to this router, all these other devices are going to get that frame if we're in a logical bus, correct? This is the hub. I want this person, this device, and this device to ignore it, drop it, and only this device to accept it. So therefore, I need to set up some kind of physical addressing. That physical addressing is only going to be pertinent to local delivery. Derek, can you do me a favor and turn my special friend there? Just got it. Thank you. All right. So in order for me to establish this, I'm going to give some of these devices some addresses. Let's just say this device has an IP address of 192.168.1.10. And it's going to have a MAC address of 0A123B. Let's see. When do I stop? How many more places do I have to go? Remember, this is in hexadecimal format. You can tell because I see some letters going on. I have 4, 5. How many more? Am I good with just these? 1, 2, 3, 4? Tell me when to stop. Am I good now?
Yep.
Okay, how did you know I was good at that point? Because I didn't put another colon. How many bits make up a physical address for Ethernet? 48? 6 times 8 gives me? 6 times 8 gives me 48, right? I have 1, 2, 3, 4, 5, 6 places. We good? Each of these places is considered an octet. Does that make sense? How many bits are used for a hexadecimal number? 2 raised to what power will give you 16 numbers? 4. Each of these are 4 bits, hence the 8 bits, right? So each of these would represent an octet. If IP addresses are only 32 bits, we have 4 octets, correct? But MAC addresses are 48 bits, hence we have 6 octets. Why are MAC addresses 48 bits and not 32 bits? Why can we get away with 32 bits for IP addresses and not for physical addresses? Are physical addresses hierarchical? They're not hierarchical. In fact, if I wanted to, which I'm not going to, I could grab this device over here, give it an IP address of 192.168.1.10. Right? This allows me to reuse these IP addresses and not worry about it. In order for me to be able to do that, what must these routers have running? What's that? NAT. Network Address Translation. I'm getting you guys ready for your exam next week. These are all highly testable questions. I am not going to do it this way, and the reason why I'm not going to do it this way is because verbally, me saying, if PC 192.168.1.10 wants to talk to PC 192.168.1.10, what are you guys thinking? If it wants to talk to itself, right? So I'm going to assign this PC 192.168.2.10. What could I assign this network down here? Whatever address. I mean, we're just learning this stuff. It doesn't matter as long as network A, B, and C do not have what in common? A network address. Correct? We have 3 networks. One is the network B. That's the WAN that connects both A and C together. This device is properly configured to have an IP address. Its physical address, which we all commonly call a burn-in address, because we cannot change that physically. We good about that? Now, I decided to implement, I'll put this over here, CSMA/CD. What does the CS stand for? Carrier sense. All these devices, because they're connected by a hub, are going to receive every frame that was ever passed onto this network. Before they can transmit, they must check to see if the carrier is available. The absence of a carrier means the medium's available, so hence transmit. So we check. If nothing's there, we wait. Then we check again. Then we transmit. We clear about that? What's the MA? If the CS is carrier sense, what's the MA? It's actually multi-access. Why is it multi-access? and not media access? Because this medium physically looks like this, but logically acts like that. And that's where all my nodes are. Correct? And so it's like electricity. If you tap that main wire in, once you put voltage on there, all the other wires are going to get it. Hence the multi-access. The medium is accessed by many users or many different devices. What's the CD stand for? All right, why is that important? Even though I told you that they wait to check to see if the carrier is available before they transmit, collisions can still happen. Why can collisions still happen? Because, I mean, after all, ideally, if you guys follow the rules of the classroom, don't talk unless what? Nobody else is, well, no, I'm not that hard. Don't ouch. I better not go any further than that. But any case, it comes down to if nobody else is talking, then you guys can talk. I don't even tell you to raise your hand. I'm very laid back here. You guys should like me. Some people say, look, you got to have your hand up for at least 5 minutes for me to acknowledge you. And you need to sign out the hall pass before you can go to the bathroom. But I just tell you, do your thing, right? Just don't be interruptive. Just be respectful. If I'm talking, listen, and when I stop, you can talk, right? Or if somebody else is talking, wait for them. But does collisions happen? Let's say if I actually wait and let you guys talk for a second, and 2 people in this classroom have a question. What do you think is going to happen? They might both talk at the same time because they both waited and they detected that the airways were available and they collided. When does that typically happen here? Further the network is, the larger the geographical space it is, the greater the chance collisions are going to happen. And this is why Ethernet says the maximum distance between an end device and another device, whether it's an intermediary device or another end device, is 328 feet. That's 100 meters. Computers don't care about distances. What they care about is time. Grace Hopper was a wonderful lady back in the day. She's the pioneer when it comes to computer science. In fact, she was a naval officer and she created the first compiler. Yep. And she was so brilliant that she went down to her engineering department, if you will, and she asked, can you show me what 1 nanosecond looks like? Folks, there is no technology out in this world that can pause every frame and show you a nanosecond. In fact, if you were to see a nanosecond, if I were to take a picture of a bird flapping its wings or a hummingbird or whatever, or even take a picture of a bullet, and if I can get it down to a nanosecond, and every nanosecond that would pass, that bullet would still look like it's standing still. That's how fast a nanosecond is. So how do you illustrate to somebody what a nanosecond is? Yeah. What she did is she asked them to cut a piece of wire, the length of a nanosecond. Now wait a minute. Seconds have lengths? How long is a second? Distance-wise. It depends on how fast you're traveling, correct? So if you're using fiber optic, a nanosecond is going to be a longer wire because light travels really fast. In fact, we almost round the speed of electricity to equal the speed of light. So that's what she did. She cut a piece of copper to show people how long a nanosecond was when you put electricity. So that in other words, when you touch one end of that cable with electricity, how long would it take, or how far would it travel in 1 nanosecond? So if this is the beginning, how far will the cable be if it took electricity 1 nanosecond to get there? Yeah, it's something like that, which is pretty fascinating. 5 to 6 inches, 1 nanosecond for electricity. So we calculate that. We typically deal with milliseconds when it comes to computing, when it comes to networking, and we say, wait 30 milliseconds before transmitting. And if you calculate that out, it's about 328 feet. So it takes electricity 30 milliseconds, give or take, to travel 328 feet.
Pretty good for its
Really fast. Okay? So that becomes an issue when we start talking about collisions, because if this waits 30 seconds and this waits 30 seconds and they both haven't realized that this person has began transmitting, this one's also going to transmit and they're going to get a collision, correct? This type of media access control method is going to say, if it does happen, let's try to deal with it, because it will happen. And the more users you have on this network, what's going to happen? Yeah, and that's not the only case. What about the more traffic that's being generated on a network? What's going to happen to the chances of collisions? They're going to go up. So the more users and the more traffic you generate, the greater the chance you're going to have collisions. What else can we do to avoid that? Could we modify the logical topology? We can do controlling. Controlling is going to say, okay, we're going to go around in a circle. Start here. If you have anything to say it. If not, pass on the microphone. What's the issue with controlled mechanisms? It could be slower. I mean, I don't like to say good and bad when it comes to performance as much as I'd like to say it offers something that takes away something, right? The reason why I say it could be slow or fast is it all is dependent on the number of users and how much data you want to transmit, especially over larger spaces. In fact, rings are really good for large geographical spaces. The fact is, when it comes to control mechanisms, if this person has nothing to say, and this person has nothing to say, and this person has nothing to say, and this person has nothing to say, but this person does, we got to start here and go around sequentially. Whereas in a multi-access network like we see right here, anybody can talk at any time. The other thing that makes it nice for these networks is it's really easy to troubleshoot and add to. Whereas in controlling networks, I know it starts here and it's all deterministic, but adding something to it, I shut down the whole ring. Because in order for people to transmit, it has to go from here to there to here to there. If I shut down this ring to add another device in there, nobody's going to be transmitting. Okay? What about this network here? Is that controlled or deterministic or non-deterministic? And if so, what type of media access control would I implement in this point-to-point network? Write this on your forearm. So on your quiz or your exam that you guys are taking next week, simply this. When is the only time that we must implement media access control? That's exactly right. When the media is being shared by more than one device. Why must I implement some media access control only when I'm dealing with shared mediums or media? And in any given environment, if it's being shared, I'm going to have to worry about collisions. I'm going to have to worry about identifications. But in a point-to-point network, it starts here and it ends there. It's extremely controlled. There's only 2 nodes on there. In fact, do I really need to bother with some kind of addressing mechanisms when it comes to point-to-point networks? No, in fact, if you look at my address, I have all ones. What have we learned about all ones? Broadcast address. Ironically, if you're broadcasting something, where is it going to go in a point-to-point network? Yeah, to the other device. Now, do point-to-point networks have to be physically end-to-end? Can we have a point-to-point network that could go from here to here to here to here? We call that a virtual connection. Let's talk about this network over here. Instead of putting a hub there, I'm going to put a switch. What does a switch allow me to do? No different than what a hub does, but what makes a switch and a hub different? Yeah, I told you guys that when it comes to a switch, it understands frame addresses. And I said the best way to see a switch is like a star topology, correct? A switch creates point-to-point networks between each of the nodes. If there's a point-to-point connection from this node to this switch, and there's a point-to-point connection from this switch to this router, and there's a point-to-point connection from this router to that router, what do you think we have? We have a virtual connection, a logical point-to-point network. Do we have to worry about collisions in a network like this? I still have to implement CSMA/CD. Why? Because collisions can occur in a network that does implement a switch. Not as often as on this network. When will a collision occur in this switch?
Everybody sent one packet at the same time.
When we're broadcasting stuff, right? Because when you're broadcasting, everybody in the switch will get it. And if you're broadcasting, there's a chance that somebody could be sending at the same time they're receiving a broadcast, so there would be a collision. So we do have to implement CSMA/CD. However, the chances of collisions happening are very few. But nevertheless, since we're implementing this technology, there is some overhead associated with it. And so we can't have a pure 100 megabits per second bandwidth. We call this the throughput, right? So given what we have here, and there's a switch connected there to connect all those local devices. This has a physical address. I want to give this an IP address as well as 192.168.1.254. Is that okay? I can just say this is .254. By now you guys understand it, that belongs to the same 3 octets. I didn't give you a subnet mask, so you guys are supposed to assume classful, right? Which class is this? C, right? First 3 octets. Make sure you guys know that by next Wednesday. All right, I need to give this a MAC address. I'm just going to say this is 1A in the interest of saving time. I'm going to come over here and give this an IP address. Why must this have an IP address?
It's a different side of the router. It's the public
Yep.
side.
Now, could I have not bothered with that and set up PPP? I would love to. But setting up PPP is beyond the scope of this course. If I set up PPP, I would not have to give it an IP address. Are we clear about that? Because I know the only place where this packet's destined to is there. Why bother with addressing? But instead, I'm going to do what we call Pppoe. That's point-to-point protocol over Ethernet. All right? And the only reason why I'm using Ethernet is because I want you guys to understand the whole routing process. So this is going to get an address. I'm going to make this one .1. What is this address going to be? .2? What's the subnet mask going to be for this network? I can actually VLSM that, right? There's no need to waste all 252 addresses. So I gave it a /30. What's the subnet mask going to be then if it's a /30? 252? It'll be 255.255.255.252. Because the last 2 bits are the 1 and the 2, right? 1 plus 2 gives me 3. 255 minus 3 gives me 252. Why did I take 255 minus 3? Because 255 would be all 1s, correct? And I'm removing the last 2 bits, which represent 3. All right, I'm going to give this a MAC address of 1B. I'm going to give this a MAC address of 2B. I'm going to give this a MAC address of 1C002355F78. 1, 2, 3, 4, 5, 6. Okay? This person wants to communicate with this person. Let's skip over layer 7, 6, 5, and 4. We'll assume a session has been established. Here I have over my model, I'm at layer 3. What does layer 3 need to know for this node to be able to talk to this node? We're going to need the source IP address, which is going to be what? .10. What else is it going to need to know? 192.168.2.10. All right, this gets encapsulated into a frame. What is the frame going to need to know? First of all, what frame are we working with? We're dealing with an Ethernet frame. So we're working with this blue frame. We clear about that? Here's the preamble. Nothing I can do about that. The LLC of the data link layer has determined that Ethernet's being used in this network right here. Since Ethernet's being used in this network, it's got to start off with 64 zeros and ones. And it's going to do it with a certain order. That's going to be for timing issues so these other devices can distinguish between consecutive zeros and ones. Just like when I had a slide that went black, black, black. How did you guys know those were 3 zeros? The timer. The preamble helps to establish the timer. It does it on the fly. But it needs a destination. Destination what? MAC. Okay. What MAC address do I give it? Do I give it this MAC address, this MAC address, this MAC address, and I'm reporting to the other router, the other MAC address of that router, which let's make this one, these are C's, we'll make this 2C. Or do I give it this MAC address of this node?
The one for the
What happens? Okay, which router? Oh. Let's stop right here. Let's assume for a second all the ARP tables are established. We have a converged network, okay? When this device has determined that it's going out to this IP address, 192.168.2.0, what will this device do? It's going to AND it with its own subnet mask. Why will it AND the destination IP address with its own subnet mask? Exactly. To determine whether it's a local device or a remote device. It is a remote device. What will the interface card now determine? What will the data link layer do? It'll say it's got to go to my default gateway, correct? It'll look at its ARP table and say that my default gateway has a MAC address of 1A dot something dot something dot something. Do you see I'm using the MAC address of my router's local interface card, the side that's connected to this network? What's the source MAC address going to be? What's that, Michael? It's going to be mine. So it's going to be this 0A colon 112 colon 3B and so on. I can't control that, at least not at this layer. This is the IPv4's binary equivalent, okay? So there's the bits. Notice there's only a 1 right here and everything else is 0. This is letting me know, or sorry, letting the other devices know that when you receive this, you must have IPv4 installed on your device. Otherwise, you're not going to understand it. Discard it. Don't waste your time. We clear about that? Everything else is established. This is my packet that I want to send, and the frame check-in sequence is going to be created. CRC will be calculated here before it leaves. Where will the frame go to next? The hub. What happens? Will the hub do any de-encapsulation? Why not? A hub is a physical device. It does not understand framing addressing. Okay? So what the hub will do is it'll copy it and send it out all the other ports. The router gets it. What will the router do with this frame? First of all, it's going to match its own MAC address with the destination. If there's a match, it's going to de-encapsulate it, stripping all this stuff off to get to the data. Well, wait a minute. How do you know the data was transmitted successfully? So what this router will do is it'll calculate a CRC. How many times we've calculated the CRC?
Each time some data is made.
Twice so far, right? Once here, once there. What will the router do if the CRC is appropriate? Strip the packet out of the frame. And what is it going to do with the packet information? Not yet. It's going to grab the destination IP address and do what with it? And it with every subnet mask in its routing table to find a what? A destination network address, correct? What is that information going to do then? What are they going to use that information for? To determine what interface on the router must the new frame be placed on. Okay? It finds a match. It's going to send it out of this. It's going to send it out of this interface. Hence, what becomes the destination MAC address? We're at this router. Where's the only place it can go to? What's the source going to be? 1B. Okay? So it re-encapsulates the packet into a frame that has new physical addresses. What else do you think it's going to create? A new CRC, right? Why? So that when this interface receives the data, it can verify that it was transmitted correctly. All right, so the packet gets passed on to this frame. This router receives it. What's it going to do? It finds a match, correct? De-encapsulates the frame. Looks at what when it comes to the packet? Destination IP address. Goes in its routing table. Says, hey, you know what? I need to pass you out of this interface. So what happens when it comes to this interface? What gets put into this frame? 1C, right? Because it's going to have an ARP table. What's the source going to be? 2C. What else is it going to calculate before it puts the frame back on the network? CRC. Now it goes to the switch. What is the switch going to do? De-encapsulates it. Grabs the MAC address, looks at its MAC table, and then passes out of the right interface. So guess what happens? A new CRC is created here, and it's also created on the interface. Let's count how many times CRC was actually calculated. Once, twice, 3, 4, 5, 6, 7, 8 times. Do you see the only address that was ever changed was the physical addresses? Do you see how we accomplish local delivery? I'll see you guys tomorrow in lab. We'll be exploring this technique then.